Hello, everybody. Welcome to episode 95 of the Hyperthesis podcast. I'm Liam.
I'm Feely.
I'm Patrick.
And I'm Monika.
As you can hear, we have a very special guest with us today. We have Monika Azmanska. Sorry.
Yeah.
Did I say that right?
Correct.
Okay, Monika
yes.
Azmanska. I realized I never said your last name before, and I forgot to double check with you to make sure I wasn't pronouncing it wrong, because I'm very bad at pronouncing things, it turns out. But anyway, thanks for joining us, Monika. It's great to have you.
Thank you for having me.
So a little background on Monika. Monika completed her Bachelor of Science at McGill University, where she worked in the field of photonics with Dr. David Cook, and her two main undergraduate research projects involve studying front-induced transitions by simulating relativistic photoconductivity fronts, as well as generating and measuring terahertz vortex beams. Monika then transitioned to experimental condensed matter physics at McMaster University, where she then completed her Master of Science with Dr. Pat Clancy, where she investigated charge order in lead rhodium oxide.
Yes, correct.
Yes,
Good.
okay. I used ChatGPT to look up what that symbol was. And then, Monika, you now are in your first year of your PhD degree in the same group with Dr. Pat Clancy, and you're currently studying structural, electronic, and magnetic properties of different quantum materials using neutron and X-ray scattering techniques. And a little fun fact is that, interestingly enough, Monika also has a minor in musical applications in technology and sound recording, which she also received during her undergraduate degree, which is something I'm definitely gonna ask about later, but we'll get there. So thanks for joining us, Monika. It's great to have you.
Great to be
And
here.
definitely critique our audio setup too.
Yes, we just spent 30 minutes troubleshooting my audio. We're having some issues, but again, we won't get into that.
That's part of it.
It only happens when there's guests, just so we can look silly. So thanks for joining us. But before we get to your research and what got you into science and all kinds of interesting things, who here has an intro topic prepared for us? Patrick.
Okay, so I have two related-ish, but equally as interesting, I would say, intertopics. I tried to find something kind of in like the field of photonics and like quantum sensors and materials and all that. Forgive me, I tried my best, but so there are two different recent findings / publications that I want to talk about, and the first one has to do with the detection of neutrinos. So as we've discussed several times before on the show, neutrinos are incredibly elusive particles that are produced in a variety of different nuclear reactions. They interact weakly, which just means they interact through the weak force for the most part, and a little bit through the electromagnetic force. But they're everywhere. They're produced in the sun, for example, and all those nuclear fusion reactions. And if you place your thumbnail flat to the sun, about 100 billion neutrinos pass through your thumb every second. So a lot of them everywhere. They're the second most common particle found in the universe. I'm pretty sure the first one is photons. So they're everywhere, but we don't really know a lot about them just because they tend to interact only weakly or through very rarely through electromagnetism. So it's hard to study them. We need these giant detectors to be able to actually detect them. So, for example, the 2015 Nobel Prize, which we have definitely talked about before, in physics went to Doctors McDonald and Kajita for their discovery that neutrons oscillate between three different types. And the fact that they oscillate means that they have mass, meaning they don't travel at the speed of light. And there was also some controversy with that. Was it 2016, I want to say, where neutrons were detected as traveling faster than the speed of light, and it ended up just being a sensor error, which, to all those out there doing experiments, make sure to check your sensors. And also don't announce things before they're peer-reviewed. Anyway, moving on. We have done a lot of different studies with improved sensitivities for neutrino mass. So one very large one is the Cattern experiment, also known as the Karlsruhe tritium neutrino experiment, which is working to define the mass of the neutrino using this massive detector. There are cool images of it moving through a small town in Germany. Definitely go check that out. But there's a lot of attention that's being paid to the mass of a neutrino, but less so to the actual size of a neutrino. Now, when we say size of a neutrino, or really any type of particle, elementary particle or otherwise, it's not a great description just because it's more so the size of the wave packet of the neutrino itself. And so we can't really describe things with size at that level, but more so the size of the wave packet. Here, I'll just be using the term size because it's easier. You've already been briefed about what size means at the quantum level and very, very tiny scales. So the best constraints for the size of a neutrino range in 13 orders of magnitude. So quite a lot of variability, not very strict constraints on the size of a neutrino. And this is something we really don't know. Like, how big is it? There's theories that neutrinos are actually the size of like a beach ball. But again, there haven't really been thorough experiments to constrain the size. But a recent paper published by Joseph Smolsky et al., there's a whole team of physicists, has now worked to at least set a lower limit for the size of neutrino, and specifically an electron neutrino. So in this paper, the experiment which they used, which has the acronym the BEAST, which I think is one of the better acronyms in any sciences, but they're using a very cool device to measure the lower limit for neutrino sizes. And to do this, they're using, quote, highly localized, unstable systems embedded in a complex solid-state material at low temperature as a precision laboratory to probe the quantum properties of subatomic particles, unquote. That's a mouthful. There's a lot going on there. The main thing is that it's using solid-state materials that are supercooled to try and measure what's happening when neutrinos are produced. I'll get into that in just a second. I will preface this by saying that other experiments have previously indirectly measured the size of a neutrino, particularly looking at the effects of particles that result from high energy collisions or whatnot, but they rely on the standard model. So this indirect observation of the neutrino size comes based on the assumption that the standard model and how it describes neutrinos is true.
So my guess is that usually I don't know what they mean when they say cold, because depending who you talk to, they have very different definitions of what is a low temperature. But usually you do low temperature things because you don't want to worry about thermal effects or background noise or other things like that. So if you get rid of all that stuff, somehow they believe that a neutrino can probably interact with some quantum-y part of the material and get a signal or something from it, right? Maybe?
Yeah. So one is to reduce noise, of course, but the other is just to make sure the material, the solid state material that is being used is superconductive. So superconductivity plays a very important role here. So you're absolutely right. It limits noise, and having things very cold limits that noise even more. But in this case, what they were working on is having this essentially layers and layers of different materials. I won't get into them, but the top layer is superconductive at, of course, very cold temperatures. And then they embed beryllium-7 on that.
Well, I was just going to say, most superconductors, as far as compared to what I do, they're so warm. They're very hot. I think everything I do is in like the nano-Kelvin range.
Yeah, by the way, people like Liam are few and far between. It's just very few people will say it like, oh yeah, it's only 70 Kelvin. Man, that's so warm.
That's like, what, 10 to the 9 times warmer than what I'm doing. Anyway.
Yeah.
Okay.
So probably warmer for what you're doing. But I mean, the temperatures they're dealing with are about 0.1 Kelvin.
Oh,
so I don't
that's
think
not
too much
bad.
warmer.
A little chilly.
It's only 10 to the 8 times hotter than what you deal with.
Yeah, exactly.
Yeah. So there's supercooling this certain material. Again, I won't get into the whole manufacturing process, but essentially they made this sensor, put beryllium-7, which is radioactive, on it. And so what they're looking at is they've chosen certain materials so that any energy input into the system can be detected over a certain threshold. And I think it's something super small, like 0.7 millielectron volts. So quite a small energy can be dumped into there. And so in the case of something like a nuclear decay for beryllium-7, it's able to detect that energy essentially by measuring the recoil of it. So when beryllium-7 turns into lithium-7, it goes through the process known as electron capture, and that electron capture an electron is absorbed within the nucleus by a proton that turns into a neutron, and as a result, a neutrino is released from that, an electron neutrino. And so they're able to essentially say, okay, we're going to measure these decays by looking at how much the newly created lithium-7 recoils from this nuclear decay. Again, I won't get too much into the experimental procedure and how exactly they did this. Just a cool note is that this device, so this sensor device, was produced in at the Triumph facility in Vancouver, Canada, and calibration was done using the UV laser for the actual to understand what energy input gave what signal.
Well, it's I was thinking you're going to come up with photonic intro topic, but you always somehow relate to particle physics. And the thing about these things is like, oh yeah, we got to try to detect neutrino. Well, they aren't really detecting neutrino in the practical sense, right? Because what you want to detect is the byproduct of the interaction from neutrino, because you don't really capture the neutrino directly, because they don't interact with light, for example. So most thing they try to find is to capture the smallest light of photons that emit from things that, your interactions and such.
If you drop an apple, did you detect gravity or its effect? Right?
That's a good point. And in this case, they're detecting the effects of the production of the neutrino. But in this case, it's, I guess, not direct detection of like the actual size of the neutrino, but what they did was they looked at the different energies. So when beryllium-7 decays into lithium-7, there are 4 different energy peaks. They looked at one of those particular energy peaks that had a very clear signal in their device. And they were able to determine the energy of the recoil with an uncertainty of only like 2.9 electron volts, which is super small for these types of measurements, considering this decay happens at a much greater energy than 2.9 electron volts. And then what they did was they looked at the conservation momentum and the conservation of energy. They approached it from these 2 different sides and said, okay, based on the energy that's deposited into the neutrino during the decay process, they were able to set essentially 2 lower limits for the size, because they used the uncertainty principle and again just looked at the energy and momentum, and then found the more conservative estimate for the size of the wave packet was around 6.2 picometers. Now that's still quite small. It's not beach ball size, but this is just a lower limit, and it's actually larger than an atomic nucleus itself. So really interesting results here. And I did promise there would be a little bit of photonics. So the second topic that I'll talk about very briefly has to do with the fabrication of superconducting nanowire single photon detectors, or SNSPDs. really rolls off the tongue there. But these ultra-thin wires are superconducting, but when a photon interacts with them, they change to a resistive state. And then by measuring changes within the voltage, there's a bias that's applied to that nanowire. By measuring changes, when it becomes resistant, you get a very effective single photon detector that's quite accurate, and it can also be quite fast. Now, these devices require some very specialized manufacturing and requires a combination of nanowires to actually interact with the photon, optical microcavities for the photon capture, and then this kind of keyhole-shaped chip that aligns the detector with an optical fiber. And so the size of these detectors is usually on the order of nanometers to maybe micrometers, but the manufacturing process is tricky. In addition, these wires have to be arranged in a particular way, known as I think it's piano art fractal pattern. So complicated patterns to manufacture in something like a nanofab, and they are used to detect photons. And this specific art fractal pattern is able to detect photons regardless of polarization or direction. So that way, it's kind of a universal photon detector instead of needing a certain type of polarization. So a recent publication in the IEEE Journal of Selected Topics in Quantum Electronics, which we have linked below, authored by Kai Zhao and Xiaolong Hu, outlined a scalable manufacturing methodologies for these SNSPDs at both the nano and micro levels, which essentially the method that they employed makes it a lot easier to manufacture these types of sensors and a lot more clear-cut. They even have suggestions for different types of uses and how you can tweak the manufacturing process for those different use cases. And I wouldn't get into manufacturing details. I've already been scolded for turning this into a particle physics thing. But it's really interesting. I kind of fell down the rabbit hole of looking at SNSPDs, and I don't know if we'll talk about them more, but it's just really cool to see how they operate just through a decently simple principle, and the fact that new manufacturing techniques are coming out that makes them a lot more useful, and especially in things like quantum optics or quantum computing, making these manufacturing processes easier, more accessible, and simpler in terms of the components and the steps needed, will really kind of help expedite the use of quantum computers and also ensure increased efficiency and sensitivity. So yeah, just a couple updates. I did turn it back to photonics, but yeah, just some cool stuff in the news recently.
Well, thank you, Patrick, for the interesting topics. Now, for the main topic, we are going to give Monika a quiz. No, I'm just kidding. We're going to ask you some pretty basic questions. So, Monika, can you tell us about your current research and maybe these intro topics Patrick gave us? I think they're going to motivate some good questions, at least from myself, because as he was reading off those intro topics, I remember I had a few like, oh, I wonder how that type of thing applies in Monika's research, and so before I guess I can ask that. What do you do? Tell us
Yes.
about your research.
So right now, I just started my PhD. So I've started new projects, and I'm also continuing projects that I had started before, and they weren't directly into my thesis. But right now, I'm working on these materials called mixed B-site pyrochlores. So pyrochlores are specific materials that have this interesting geometric shape. They're basically this network of edge-sharing tetrahedra, and they have these really interesting properties. And you get these mixed sites. So you get an A site and a B site, and then in the B site, you can introduce some disorder. And then from that, you can look at the kinds of magnetic properties. You can tune magnetic properties and electronic properties of that material. Another project that I'm working on is looking at hydrogen storage materials. So we're working in collaboration with CanMet materials, and they synthesize a lot of different kinds of alloys, but more specifically titanium, vanadium, and chromium alloys. And so what we do is we characterize these alloys, and then we look at whether or not they're capable of storing hydrogen. So these characterizations are done through X-ray scattering and neutron scattering as well. So with neutron scattering is extremely sensitive to hydrogen and to the presence of it. And so we're looking for these hydride phases. So that's also a really interesting application that we have. And so I'm currently trying to develop these projects and then looking for new things. And another project or another type of materials and class of materials that I'm extremely interested in is high entropy alloys. So these are these kinds of materials where you can introduce, so for something to be high entropy, you need to have more than 5 elements that are competing to exist at the same site. And so what happens, interestingly, is that this high entropy actually contributes to the cohesion of the material. And so it's a very new subject, and it's really interesting for things like thermoelectrics and semiconductors as well.
I have a pretty naive question about the hydrogen storage project.
Yeah.
Why does one want to store hydrogen?
Yes,
I'm sure there's many answers to that, but
So I'm going to go with the most basic explanation is that hydrogen is thought to be potentially the future of energy. So you can get some really clean energy. I don't really know the exact processes of extracting energy, but basically right now, the problem is storing hydrogen, getting hydrogen from one place to another. So to be able to do that, you actually need to store it in these really big volumes so that it doesn't explode. So the idea with solid state hydrogen storage is to create these materials where you could create these cavities and then embed hydrogen within these cavities and make it not interact with itself. And so then you can, store a significant amount of hydrogen without caring for having these, big volumes, and also reducing any chance of explosion.
Okay, so you can increase its density, but just put little walls between them all, like a little jail cell or something,
Exactly.
like a jail.
Exactly.
So that they don't. Okay, that's kind of cool.
Well, from what I hear from the description, it sounds like you're in a chemistry department. So which part is your work? It's physics.
Yeah, so that's a really interesting question, actually, because quantum materials and condensed matter physics, we do end up doing a lot of chemistry-related things. And not that I have anything against chemistry, but I did go into this and into physics. And at a certain point, you think, wait, hold on a second. I'm doing chemistry at the moment. But I think the difference is, I guess, the modeling, the data modeling. We have a little bit less of an interest in the synthesis, although that is part of it. I guess it's the characterizing and then looking at the actual interactions that are happening within these lattices and, between these sites. So what are the competing interactions? Essentially, that's what a quantum material is. So it's a material that, presents really interesting macroscopic properties because on a microscopic level, you have a bunch of interesting competing interactions. So we're essentially more focused on the physics side of things. But you can argue that there is quite a bit of an overlap with chemistry.
So when you're looking at these materials through using X-rays and neutrons, are you looking at the dynamics of, say, hydrogen diffusion through them? Or are you just kind of looking at them where there's hydrogen stored in there, if there's hydrogen stored in there, if there are any other adverse reactions happening? Or are you looking at we're say pressurizing a system, or I'll probably ask more about this, but we're actively putting hydrogen in there and then measuring the changes within the structure or contents or things like that. So I guess, what are you looking at specifically?
Yeah, so that's a really great question. Two things. The first is that we are looking for signs of a hydrogen. So specifically with neutron scattering, you can see these specific hydride phases that appear as peaks in intensity at 2 theta. So we're looking at for that, for seeing any kinds of peaks within the data. And what's interesting with titanium, vanadium, chromium is that in neutron, so when you're doing neutron scattering, the scattering factors of these materials are very low. So essentially, you're just looking at background. There's no peaks in neutron scattering. So it is very easy to identify the presence of hydrogen within these materials, if there is any at all. And you would expect to see something if the material itself has an increase in mass. So then you try to figure out whether or not the mass actually does mean that there's hydrogen in it. So that's the first thing. The second thing is that hydrogen contributes to incoherent scattering. And incoherent scattering means that you don't necessarily see a peak, but you would see an increase in background. So that's also something that we look for. So comparing, non-hydrogen loaded materials with hydrogen loaded materials, seeing if there's any difference within the backgrounds, within the mass, things like that. And then secondly, looking at the structure of the material itself. So these alloys tend to be BCC, so body-centered cubic. When you look at the material, when you look at the structure of the actual crystal, and once you input hydrogen in it, and hydrogen occupies these cavities that exist within these crystals, we expect there to be a structural change. And that structural change should go to FCC, face-centered cubic. And that's something that you can identify through X-ray scattering. So you can figure out what the lattice parameters are. You can figure out, you can do some refinements and then see, we're looking for changes in structure of the material. So those are the 3 things that we're looking for. And then, and then the way that we look at it is also comparing the different kinds of ways that they try to induce or put hydrogen within the material. So as you mentioned, yes, pressurized cells, but whether we're working with powders or chunks or solid materials, things like that.
Well, you mentioned that you don't deal much with the synthesis side, but I'm studying subassembly of a lot of these structures. I wonder, in the quantum materials, what are the types of techniques people use to create, like you said, the arrays of tetrahedras, for example? Are they using subassembly to create these? Because one of the good things about subassembly is that you just leave it alone and it will form by itself, or is there specific techniques that people use in your field?
Yeah, that's a great question. So there are many different kinds of growths. So for that specific project, I don't focus on synthesis. However, I do have other projects where I do participate in synthesis, and that would really depend on how the material grows and what you want your material to look like. So whether you're going for smaller crystals or larger crystals. So for neutron scattering, you would want to have a larger crystal, whereas for X-ray scattering, you'd want something that is smaller. So there's many different kinds. So there's something that's called flux growth. So that essentially you have flux of something, and then it's a chemical reaction, and you put it in a furnace, and then you're just following a recipe. That's one way. Another way of synthesis is floating zone growths. So you might have heard of this, that essentially you have a seed rod, and then you can have a bunch. So there's a lot of different kinds of ways that you can do floating zone growths, but I think the way that we do it is with halogen lamps, and then you melt the seed rod onto another rod, and then you have a single crystal that forms. Other synthesis techniques. So for the titanium, vanadium, chromium alloys, there is what was it called? Yeah, I mean, you can do SPS, so spark plasma sintering, not for those alloys, but for other alloys. Yeah, there's many different kinds of ways to grow things.
Yeah, this is completely foreign to me, even though I do theoretical
Mhm.
and computational stuff. So if I want to have an X-ray diffraction, a diffraction pattern, I run a script, and it's like, here's the diffraction pattern. I get a Borner diagram. I get what I want by the computers. So I have no idea how people really grow these stuff in the lab, because in computers you can put things in a lattice with just a bunch of computer codes, or you can make it so that it's self-assembled, or you can cool it down, use simulated annealing. There are a bunch of tricks. You can do molecular dynamics, you can do Monte Carlo simulations, and all bunch of stuff. But when it comes to what actually people try to make in the lab, we just said, hey, please, sir, chemist or ma'am, could you make these in the lab for us? And most of the time, it's like it's interesting how it's like puzzles that they solve. Like, well, you want to create these certain shape of the crystal, certain structures. There's specific techniques, which I don't really know why people prefer one over the other. But it's nice to hear that there are a bunch of stuff that these bags of tricks that um, experimental physicists and chemists do.
It's a lot of trial and error, I would say. And there's a lot of going back at literature, reading these protocols and trying to follow what they've done. And then, you can dope your material, or you can play around with the temperatures. And again, it depends on many different things. It depends on whether you want something that's homogeneous, whether you're growing powders, whether you're growing single crystals, how large do you want your single crystals?
So I think there are two questions that come from it. First is like, how do you test the purity of your sample, or do you even need it to be pure? Because one of the problem is that, well, we grow a crystal, perhaps there are other crystals that are forming, or how do you know it's only one type of crystals, or how you prevent that? Or maybe, if you only have the certain material, because I know like some materials can have many different crystal structures, but you want the specific ones. How you know it's pure?
Yeah, great question. So there again depends on the kind of material that we're growing. If you know what the magnetic properties are, or what you would expect your pure material to have, then you can do macroscopic measurements for their bulk properties. So you can measure their magnetic susceptibility using a squid, which is a really fun name. Or you can also just do powder refinement again. If you have a single crystal, depending on how large the single crystals are, you can look at them at the microscope, and that's also a complementary way of figuring out whether something looks like a crystal or not. And then single crystal XRD, see if you get something that is twinned, or if it's a single crystal, or if it refines to a structure that is something that you would expect. If it sees the elements that you're seeing, that you're expecting to have from, again, there's a lot of theory there. So calculated form factors and things like that. So purity is definitely an important thing, because say, for instance, if you're doping something and you care about the oxidation states of your material that you have, then if something is impure or pure, you might be introducing additional magnetic moments, or you might be introducing additional disorder. And so that would skew your data.
I see. So, in theory, a lot of times what we try to find for any material is the phase diagram, because it really helps everybody, right? So if you want, I want this structure, maybe you increase pressure, or you took this trajectory. But like, there are so many materials around the world. And in what you do you have phase diagrams, or is it just like, well, now we have to go through like heuristic process to figure out how to synthesize this? Or is that usually a guiding phase diagram that said, hey, if I want to go into, let's say, this structure or this liquid phase, I need to do this, like increase pressure, decrease temperature here, or or is it the more heuristic process?
Yeah, so I would say that it's like an adventurous process, and depending on the kinds of materials that you're working on. So say if you're working on cuprates and high temperature superconductors, that's a pretty well-known phase map. But there are still, places on the phase space that, you can think of as unknown, and that's the land of the dragons. And then you can think of different kinds of experiments and look at, see what does pressure do, what does what does strain do, what do things like that do. You can introduce different kinds of temperature. So depending on the kind of material, some, again, experimentally, these are all different kinds of experiments that have been done, and people report their results for the different kinds of parameters that they're varying. So, or you can start off with a material that people don't really know much about, and then say, if you've decided that you want to see how pressure, what does pressure do to the structure, to the magnetic properties, if you have a material that, you're changing its crystal field, so you're changing the way that the oxygens around the metal cations interact. What does that do? So definitely a big part of what we do is mapping out this phase space experimentally.
It's really interesting how the solid state crystal people, at least at McMaster, I'm sure it's similar other places, but you guys kind of do everything, right? Like you do theory because you need to know kind of what you're looking for, and the phase diagrams and things, at least like what they are theoretically compared to what your experiment's getting. You need to know how to grow things, or at least some people nearby do, how to like grow the crystals and you need to know how to use detectors. You need to be a particle physicist because you're using like X-ray and neutron sources, because McMaster has a nuclear reactor. So we have like this really convenient source of neutrons that you can shoot at crystals and see what happens. And you need to know quantum mechanics for the crystals. You need to know optics. You kind of got to know like a whole bunch of different things in one field, and then how to like make the experiments and whatnot. Like I don't know. It just seems like a lot of stuff.
I love it. I think it's a lot of fun. At first, sure, it is a lot. There's a lot to learn, but it really does feel like a puzzle, and you have all of these different kinds of puzzle pieces that come together, and it's an extremely rewarding experience to finally see how things that I've learned in my undergrad, exist in real life.
Yeah, the CMPO, the condensed matter, photonics and optics, they are the mother of rabbit holes in a sense, like, because there are so many fields. If you want to look at crystal structures, like there are so many, and you can go into group theory or the crystallography or all this stuff, and you can spend your entire life in it. But if you want to do anything practical, like you got to learn a little bit of that and learn a little bit of everything else, right? And I wonder, on the more application side of things, I don't really know much about quantum materials, but I know that there are people try to use these days with nonlinear optics, those kind of like nonlinear crystals. Is your work related to anything with photonics in terms of like lasers or building semiconductors that may be tunable or something like that? Or like what exactly you want to do with your quantum materials?
So I would say that, so each project has a bit of a different approach to things. And that's the really cool thing about each quantum material. And the way that I try to understand things is that each material can tell you a little bit more about the physics of the materials in general. So you can, tune different distances just by changing the elements within a material, or by looking at the geometries that exist within a crystal. So to go back to the point for, what are we trying to do with studying all of these quantum materials? A lot of different things. For photonics, I haven't done anything in my grad studies, but during my undergraduate studies, I had some computational work where one of the projects with the relativistic fronts. So that was looking at these semiconducting waveguides and, using a probe pulse technique to create these essentially mirrors. So you pump the material with a pulse, and you get these wavefronts that have at a certain angle, and you can control the speed of these incoming wavefronts. And then on the other side, you can send in a light pulse and then, send it and have it interact with this front. And then essentially you're looking at how does light interact with a mirror that's moving at these relativistic speeds. And so again, this is like a photonics versus and semiconducting problem. And what you end up seeing is that you can manipulate light. That's a different outcome. You can get frequency shifting, you can get time reversal stuff. Really cool things happen there.
My experience with optics and nonlinear optics and condensed matter physics is that people a lot of people just try and understand things. They don't have any particular, some of them a motivation, some of them they just want to know what happens when you do this particular thing. But there's so many applications for it. And, if you ask me what are these applications, I'd say I don't know. But I know that anytime I see some particular thing, they've just got like pages of applications of things it could be used for. A lot of like quantum information stuff, a lot of like signal processing, detectors, tons of things.
Then I wonder, would you say that quantum materials are considered like new materials? We have something like water where not everybody, a lot of people studied water over the course of centuries, and it's still being studied to this day because some would say, well, we still don't really understand how water works. But are these quantum materials considered like a novel material, something like, what Liam studied, like Bosch-Einstein condensate is kind of the new thing and the new hot topic for some people. But I would say the more people excited about quantum materials than BEC. Well, not to shade, but would you consider like a quantum material are much more unexplored in terms of like the field itself, or are there so much extensive research already where we understand mostly what's going on with quantum materials? Like we understand mostly how water works. There may be some niche area that we don't understand, but like how explored are we in terms of quantum materials?
Yeah, so I would say that my answer to that question is yes. So yes, there are novel materials that don't exist yet or that we're looking to develop. And again, there's a lot of phase space there. So you can dope a lot of different kinds of materials, or, these high entropy materials are also a very, very new topic, and a lot of unexplored materials are there. But then also there are materials that, have existed since forever and we don't really understand, or we've only just recently started to understand. So for instance, my project for my thesis, I was looking at this electronic transition in a material called lead rhodium oxide. So at approximately 180 Kelvin, it undergoes this transition where its resistivity increases very abruptly at 180 Kelvin. And this material has known to exist since, the 70s. And no one knows why. No one knows why this transition happens. And they know that at high temperatures, they know what the structure looks like. They think that it might be because of, the conducting properties might be because of the fact that it's a mixed valent material, and that the ions and the electrons communicate with each other, so you can get electron transport. But below this transition temperature, no one knows what the structure does. So I refined the structure, and there were hypotheses that potentially maybe charge order would be happening, and so maybe that would be the reason for this this state of non-conducting state. But from my research, I saw that there really isn't any sign of this charge order. Another example for a material that's really well known but wasn't really understood until 2012 was magnetite. So, or iron oxide. So this material has been known to exist for forever, and it's thought to be the first Verwey type material. So it has these iron 3+ and iron 4+ ions within it. And until 2012, I would say, people did not know why it would undergo an electronic transition. So similarly to lead rhodium oxide, at 120 Kelvin approximately, you would get this abrupt increase in resistivity, and people did not know why that would happen. So again, there's a structural change above this transition temperature and below the transition temperature. But they didn't know what the low temperature transition was. And I was reading literature from the 1920s, beginning of the 20th century, where people would give their hypotheses and have their calculations for different kinds of ground states. And it was only proved in 2012 with different kinds of refinements, single crystal refinements of what the ground state was and why this electronic transition was occurring.
Wow, it seems like, there's a lot for you to explore, like infinite amount, because you can just, this set of the materials you can make are combinatorically large. So you have work for the rest of your future generations, I would say.
One thing I've seen before too is that like you get some not necessarily what you're doing, Monika, but I've seen like solid state physicists who were very interested in how to create certain kinds of crystals, and they would do one experiment and get like 10 papers out of it, because it'd be like one paper's on how they made it, one paper's on like other like optical properties, and one paper's on magnetic properties, and the experiment took forever to do, right? So it's not like they just spent a week doing something and got a ton of papers out of it. But yeah, there's a lot of different things you can do with the crystals, have different arrangements, different atoms, and some of them are more basic than others, but there's some pretty wild ones. So your supervisor, Pat, like he must study many different kinds of things, because I just had a quick scan through his Google Scholar. Fun fact, Pat Clancy, Monika's supervisor, who she works with, he went to the undergraduate university me and Feely and Patrick did. So we have that in common with him. He's published with one of our old profs a few times, actually, Carl. So I bonded with Pat when I first came to McMaster over that. But yeah, he's like, you go on his Google Scholar and just scroll, and there's just like all these different like kinds of molecules and crystals and things that they like, spin ices. I don't even know what a spin ice is. Like, there's all kinds of wacky exotic materials that people study. I call them wacky, but they're very interesting.
Well, I mean, not only you can study what's new material, you can take old material. Like, what if you dope it? What if you add other material into it? What if this? So there's the space that you can explore is large.
One thing, Pat does a lot of education stuff, I've heard. So he does like education research kind of on the side of his neutron scattering and exotic matter research. Or have you ever been involved in that, or did you ever think about it or talk to anyone about it? I just am interested because I know that he has at least one student who that's kind of like their main project, I believe, is education, like physics education research.
Yeah, so I personally don't have direct experience with that, but I do know that every summer we have an undergraduate student who thinks about potentially developing new experiments for courses, for undergraduate courses, or I think even somebody was working on a new undergraduate course too. So that's really cool, because I think it's really important to have exposure. I do care about outreach, which is a different kind of education, I guess. I work with Let's Talk Science. So I was a volunteer for a year, and then I was an educator and partnerships coordinator for another year, and I'm actually now the McMaster site leader for Let's Talk Science at McMaster, and it's a lot of fun. And anytime I've had any questions or any ideas, Pat's always been there to help out, and he's got some. And actually, I know that he himself, back in the day, has also participated in Let's Talk Science, and he's been a volunteer, and he'd tell me these wacky stories of, this wouldn't be legal anymore, but they would transport, liquid helium and I don't know, make ice cream or stuff at high schools and elementary schools, and I just can't imagine making volunteers do that nowadays. But yeah,
I know that when we were undergraduates, we went to a small university, so we got to be TAs very early on, and we would go around with cups of liquid nitrogen, just like fling it on
Yeah.
the floor and stuff, and see it beat around. That feels like the advanced version of that, just going around with
Yeah.
liquid helium and making ice cream.
Oh, not just advanced, expensive.
Yeah.
Well, but I want to pivot into your life a bit. So, what got you interested in, these type of condensed matter physics or quantum material stuff?
Yeah, so it's a very non-linear trajectory, I would say. I've always loved science as a kid, and I think one of the first books that I learned to read was an astronomy book. I remember going to bed every night, and my dad and we'd be practicing reading together, and it was a kid's astronomy book. So I've always really liked science. And then when I was in high school, I just really liked physics, and I didn't necessarily know what I wanted to do or what kind of science I wanted to do. And I felt that physics was the most general one out of all of them. And so I thought that, I'd start off in physics and then see eventually where I want to go for my undergrad. So that's where it started. And then I went to a bunch of different conferences, just not as a speaker, a participant. At McGill, there were different kinds of conferences where you could go as a student and just listen to different speakers. And one of them was an astronautical conference. And there was this professor, his name is Andrew Higgins, and he was in the Department of Mechanical Engineering. And he gave this really cool talk about interstellar space travel and developing interstellar space travel using, a laser on Earth, and that would propulse a light sail and then get it to accelerate to, I think it was 0.9 C, and then have it, really go outside of the solar system and do these really interesting things. And so I went up to him and I did some research with him. So from there, because I was the physicist in the mechanical engineering department, he gave me this problem, which was, you have this interstellar light sail, and it would be interacting with dust grains, going to these relativistic speeds. And so as it would interact with the dust grains, it would vaporize. So we wanted to find a way to get these dust grains out of the way. And the question was, would it be possible to use the residual light from the light sail, or from the laser that's interacting with the light sail, that's propulsing the light sail, to ablate the incoming dust grains? So that was a diffraction problem. And that was an optics problem. So I started talking to other profs to ask for optics, ideas. How could I simulate this? And this was me discovering Fourier transforms and discovering diffraction profiles. So then I got into touch with David Cook, and he gave me some tips and tricks. And from there, I ended up actually working on the relativistic front problem, which is very similar to what I was doing before. But that's how I got into the photonics. And then from there, when I was looking at, different places to apply for grad school, I was definitely interested in quantum optics and in quantum materials. So I thought that lasers were really cool. But at the end, I think I decided to go to quantum materials because I really liked the idea of going to these facilities. So in our group, we travel a lot, and we go to the States, we go to Triumph, we go to CLS, Oak Ridge, NSLS2, and it's just so cool to go into these large scale government facilities. And I think the first time I went in, I thought, who let me in here? you know? But it's just a lot of fun. I think I just ended up being in condensed matter in a lot of small ways, but I'm happy to be here.
I see. I think you've been pretty humble in your stories because like it's not like someone in high school like, yeah, let's go do physics. You must be pretty excellent at mathematics to think that too. And these professors, they just don't just take nobody, right? You said you just come to them, yeah, just I just walk up to them and just do research with them, and you must be a pretty good student too, right? So it's like, wow, this is the way you put it is, it takes a lot of different set of skills too. You have to be pretty good at academia. You somewhat have to be pretty sociable or agreeable to be able to work with to get research jobs as an undergrad in a bigger university too. So I feel like the story has a lot of you discount it a bit, but yeah, it sounds like a non-linear story, like you said. Some people go to grad school because they do really like a standard path. Nothing wrong with that, right? But having a lot of research experience really helps you decide what to do. And maybe you would change again because a lot of people change their trajectory maybe after the PhD, during your PhD and such, because now you see that there are a lot of options per se in the fields in quantum material, or even something that's like the skills you have in the labs are really transferable, if especially in your experiments. Because I think almost all of us, just me and Liam, who are theorists, realize that well, it's kind of difficult to transfer these skills in it. But like when you know how to work with a lab, you have some standards into like synthesized material, how to deal with, let's say, potentially toxic material, all these stuff. Like, do you have a lot of like certificates you get from like training and stuff?
Oh, yeah. That's not why I'm in condensed matter. Definitely not. But that was very, very nice of you to say. I think it's really important to have an open mind and to just be curious. And, there's a lot of interesting things happening out there. I think the certification is definitely, you want to be safe while you're doing your science. And also going back to the point that you mentioned for being sociable and having people skills, that's actually, I find that's maybe one of the most important things for research, because you can be a brilliant scientist, but at the end of the day, it's not like in the movies. We all work together and we all collaborate, and it's important to be able to work with other people, and at the end of the day, there's a lot of smart people out there, but if you can't work with other people, then they won't want to work with you.
Yeah,
Yeah.
exactly. It's like that's such an overlooked thing when people ask about like being a physicist, I find, or think about it. It's I don't know, like even way back in the day, right? Like in the early 1900s, it's like all these big names in physics, like they all talked to each other all the time, and they didn't have the internet, so they had to like send letters and visit each other and stuff. But they still made like a huge effort to do it because it's super important to get second opinions. It's important to like, um, you know, double check things. You come up with ideas when you talk to one another because you have different viewpoints and different takes on things. So I find that's yeah, I completely agree with you.
Yeah, and one of the problem, not maybe not a problem, one of the features of physics that a lot of us keep to ourselves, especially theorists, and you see a lot of hermits in the department. They would they just don't want to talk to anybody. Hey, but like sometimes you got to, and most of them just do only when they need to. But it's kind of fun, isn't it? Everyone has like quirky in a sense when you're in physics, but there are a lot of normal folks too. So the next question is the question we always ask our guests. I think you may know what's coming, but it's a loaded question because I think you explained your chronology pretty well so far. Because we have a bunch of questions on your interest in science when you're younger, but I think you answered it all at once, which is great. So this question is more on the future. What are your hopes and dreams? Like, who do you see yourself being? Yeah, I tell you, it's loaded. Do you see yourself being not in terms of time, like 10 years, 10, 20 years, doesn't matter, but like, are you seeing yourself being a professor, or you see yourself doing research in quantum materials as a quantum scientist, or you see yourself become more like a, teaching type? Like, who do you see yourself being? Or maybe you want to go to industry and make a lot of money, be the first multi-billionaire or something. Like, who do you see yourself being?
Yeah, so this is actually, I was thinking about how this podcast would be really interesting to go back to maybe in 10 years and see how things have changed and see what I thought about myself. But at the moment, I definitely see myself as, trying different things. I think at the moment I have curiosity towards industry because I like seeing things being applied directly. With teaching, it is very rewarding, but it's also a very long path to getting to professorship and getting a teaching position. Which is why I respect everyone who wants to do that. And for industry, I think that we're in a really interesting field where we can find, job positions that are very much related to our research and to what we do. And it could actually help with, solving things like energy problems. And, I think for now, I actually have a lot of interest in potentially working in the field of energy. So we'll see where that goes.
Okay, so we'll see headlines 20 years. Monika Azmanska achieved world peace by providing infinite energy to everybody.
Well, probably not, but we'll try working towards something.
Baby steps. We'll get there one day. All right. Well, thank you very much for joining us today, Monika. It was really great to hear about your research. Because we've talked a few times before, but I never really heard too much about your research in depth. So I'm glad I got to hear it. Yeah, it's very interesting stuff. And now also I have more context about what goes on at the nuclear reactor and in Pat's group. So that's also great.
Yeah, thank you for having me. This was a really fun discussion.
So before we hit you with a story that Patrick has prepared, Patrick will also... Oh, Feely is prepared. Sorry. Yeah, Feely's prepared it. My bad. Getting an angry head shake from Patrick as I said that.
We'll leave that in.
Yeah, well, yeah, I gotta live with my mistakes, right? I will be held accountable. But anyway, before Feely hits you with the story he's prepared for us, Patrick will tell you how you can reach us.
Yeah. So there are a few ways in which you can reach us, especially if you're interested in, say, being a guest on the show, or if you have questions for us or our guest, or if you just want to leave a comment and say hi. So the first way that you can reach us is through our email. We are hyperthesispodcast@gmail.com. You can reach out there with questions, comments, concerns if you have any. We like being corrected as well. We're all scientists here, so we accept some rigorous corrections. Just make sure to provide the proof of whatever it is. You can also reach out to us on Instagram. We are at the Hyperthesis. You can follow us on there to get updates of when we post episodes. You can see images related to our topics or images of our guests and their research, including Monika's research. I'm sure there's some cool images that you have, especially working with like nuclear reactors and very fun advanced materials. So yeah, I'm sure we're going to see some cool images on there.
I just had a scan through your master's thesis, and there's some good images in there too.
You can have any of them.
As long as it's cited.
Yeah, we always cite our sources. No, so make sure to follow us on Instagram. You can also send us a DM on there. If you'd like to contact our guest, if you have questions, is there a way that you would like to be contacted, or do you just not want to be contacted at all?
I can be contacted through email, through my McMaster email, I guess, for now.
Okay, we'll link that down below in the description. So if you do have questions about Monika's research, feel free to reach out. I mean, just from what you've said, you like outreach and everything. So I'm sure you'd be more than happy to answer some questions. And if we get any questions through email or Instagram, then we'll send them your way as well. If you are listening to us, congratulations, you found us. Thank you for listening. If you're listening to us on Spotify, that's what we're based out of, but we are found on pretty much any podcasting service available, including Apple Podcast, Audible, YouTube Music, which I have complaints about, but I won't get into. So whatever your podcasting service, feel free to give us a like or subscribe or whatever it is on your podcasting service. We also like to see ratings and suggestions for future topics. And share us. Feel free to share us wherever. We aren't really updated for our YouTube channel for this latest season, and that's okay. But you can check out some older episodes on YouTube with some nice, fun visualizations. So check us out on there as well. So no matter whether it's email or podcasting service, or even if like you record the podcast on a USB, put in a carrier pigeon, that carrier pigeon takes it somewhere else to share it with someone, reach out to us, share us, do whatever you need to do. And again, if you'd like to ask questions to Monika, we have posted the email in the description below.
Thank you very much, Patrick. Now for our story.
All right, so we are in the year of 2025. So, and in addition to it being the year of the snake, as we all know, I love snakes. But that's not the point. It's also the United Nations also declared 2025 as the International Year of Quantum Science and Technology. So this is your year. People work in quantum stuff, and they want to raise awareness around the world about how quantum technology is changing our lives. In a sense, we don't feel it, right? It's not like something that we really know about, that it doesn't really show up in your daily life much, but in your electronics, the things that being manufactured in this modern age, they all rely on quantum technology, even the satellites and stuff. Oh, anyway, so we're gonna talk about one of the fathers of quantum mechanics, well, which has iconic line, "Say my name." Anyone know? Wow. Sorry, I was just making a really far off joke, I guess. No, it was Werner Heisenberg. This was a Bryan Cranston line from Breaking Bad. Say my name.
Yeah, I wasn't fully paying attention until it went dead silent, and I was like, "Uh-oh, what did he say?"
Oh, don't worry, I can remove the silence. Anyway, so this is a short story on the life of Werner Heisenberg before he worked during the war. So when, the glory days, per se. Because he did end up working for the Nazi Germany, developing the atomic bombs, which it turned out it wasn't successful before the US did. But so this is a story that will make us feel a little bit inadequate, maybe a little, he got his biggest break basically at 25, and most of us are not 25. So Werner Heisenberg was born on December 5th of 1901 in Würzburg, Germany. So he was a German physicist, and some could say philosopher, who discovered in around 1925 a way to formulate quantum mechanics differently. So at least he formulated internal matrices, basically. And he got the Nobel Prize in 1932. And he's also the one with the name attached to the uncertainty principle, the Heisenberg's uncertainty principle, which we all know and some of us love. So Heisenberg's father, August Heisenberg, he studies Greek philology. So philology is not philosophy. It's like the love of words, philology. So study words in ancient texts. And so he studied Greek philology and Greek literature. And he was a teacher and lecturer at University of Würzburg. So Werner's mother, Anna Wecklein, I hope I don't butcher the German, was the daughter of the rector of the elite Maximilian Gymnasium in Munich. So when August Heisenberg became a professor in Greek philology at the University of Munich, Werner Heisenberg, his son, entered Maximilian Gymnasium and really impressed the teachers by his mathematics skill, and then joined the University of Munich in 1920. So in a student of Arnold Sommerfeld. As some of us know, Sommerfeld do a bunch of statistical stuff too, I think. But Sommerfeld was an expert in atomic spectroscopy. And also at the time, the quantum mechanics was being developed because the idea that things are not continuous and take on these like discrete values, which we call quantized value, which kind of developed a lot by the physicist Niels Bohr in 1913, Danish. And with that, in 1923, Heisenberg completed his doctorate, but not on quantum mechanics, but on hydrodynamics. So one of the things Heisenberg is known for is also fluid mechanics, fluid dynamics, and such. So in 1925, a couple years after he finished the doctorate, he visited Bohr's Institute of Theoretical Physics at the University of Copenhagen and found out, hey, let's work on quantum stuff, where they basically work on the problem of these spectrum intensities and try to explain it using vibrating systems. So that's kind of the birth of the quantized system. And he posited that all these theories should be based on quantities that are observable. And with these investigations, it becomes the pillar of his paper in 1925. That's not only just him. So Heisenberg formulated how to do multiplication basically in quantum mechanics, reaching linear algebra and matrix algebra. So Heisenberg, Born, and Jordan, our last name, they basically submitted a paper for publication in 1925 in September, simply called On Quantum Mechanics. And by November, Born, Heisenberg, and Jordan completed On Quantum Mechanics 2. These are translation. I think in German, it's going to sound very cool. But this Quantum Mechanics 2 paper is known as the three-man paper, which is known well as the foundation document for the new quantum mechanics. I think Schrodinger's further later on proved that all these formulations are essentially equivalent, which they should be, right? So there'll be no problem in terms of the fit. And Heisenberg, after the publication, returned to Bohr's institute. And then he talked to Bohr, and then they have another paper on the perceptual content of quantum theoretical kinematics and mechanics. And basically, he outlines the uncertainty principle, which becomes one of the most well-known quantum mechanics feature. So it demonstrates that the position and momentum cannot be exactly measured simultaneously. So this relationship of uncertainty or indeterminacy exists, where it's had to do with when you measure one thing, you have what's called delta x times delta p is more than equal to h bar over 2. Right? Everybody knows that because this is such a pivotal result. So in 1927, so when he was like 26 years old, we feel old now, won't we? We passed our prime now, I guess. So Heisenberg took up a professorship in Leipzig, in Germany. So and with Dirac, Jordan, Wolfgang, and Pauli, he started to research quantum field theory, which Liam loved very much. So So uniting this quantum mechanics with the relativity theory, or like what's happened when things go relativistic, and people to this day still work on that. So try to comprehend the interactions of particles and forces and fields, which also lay foundation for particle physics and how we perceive particles, elementary particles, how they interact. And also Heisenberg looked into the theory of atomic nuclei when after this discovery of neutrons in 1932, developing models how protons and neutrons interact. And later on, we know it's described as strong force. So this guy really put fingers in every pie. And in 1932, Nobel Prize for Physics was given to Heisenberg. And while the next year in 1933, Schrödinger and Dirac also got a Nobel Prize. And later on in his life, Heisenberg was forced by the German government to work for the atomic program for Germany. But we all know how that ended. Well, but that's the story of the glory days, the early years of the Heisenberg's life, which, as someone who kind of passed that age where he won the Nobel Prize, feels a little, maybe that's called genius. I'm just an average person and just a common folk because I ain't no publishing under certainty principle at 27 years old.
I like to think we're doing the harder stuff now. We're solving all these different Schrödinger equations and going beyond. And maybe that's just me trying to make myself feel better about it, but coping.
Right. They just figure the easy stuff, right? Isaac Newton, gravity, everybody knows that. But they have more limitations. They don't have computers. They don't have the TI-87 calculator, which is the holy grail calculator.
God,
right? They have to use.
They're on 87 now.
I don't know. I just made up that number. But
that makes me feel old if they are.
Yeah, it's like when they use abacus. I don't know. Actually, there's probably a lot of mental math and writing things down. But that's the story for today. If you want to read more about the World War II and the life after, feel free. But so for us, I think we're gonna stop here and leave the rest to the history folks.
Thank you very much for that story, Feely, and thank you again, Monika, for joining us.
Thank you.
All right, thanks everyone for listening, and we'll see you next time. Bye.
Take care.
Bye, everyone.
Bye.